Okay, let's go ahead and get started. So today I want to begin our discussion of cosmology. So as we began discussing last time, our understanding of cosmology really stems from the Copernican principle, which is the idea that the laws of physics are the same everywhere in the universe, which allows us, by understanding the laws of physics here on Earth, to draw conclusions about the structure of and evolution of the universe as a whole. So when we talk about the laws of physics being the same everywhere, and space looking roughly the same everywhere, there are really two things that we could mean by that. I'm not sure if I spelled that correctly. But the first thing that we could mean by space being homogeneous or homogeneous, but by space being the same everywhere, is that space is homogeneous, meaning that there is no preferred point in space. And the second thing that we could mean is that space is isotropic, meaning that there is no preferred direction in space. And if you think about it, these are really not precisely the same thing. So for example, we could imagine a system where you have an electric field which is pointing up everywhere in space. Then every point in space would be the same, but there would be a preferred direction, namely up, that is picked out by that electric field. And on short scales, of course, the universe is neither homogeneous nor isotropic. But on very long distance scales, where one averages out over all of the stars, galaxies, and so forth, our universe appears to be spatially homogeneous and isotropic. Of course, however, our universe is not isotropic and homogeneous in space-time. So, as we have learned in relativity, space and time can be treated on a roughly analogous footing and can be viewed as different manifestations of one single concept, that of space-time. So you might expect that if the universe were homogeneous and isotropic in space, it would also be homogeneous and isotropic in space-time. However, that does not appear to be the case. Indeed, in our universe, there appears to be a preferred direction in time. In particular, our universe is expanding as time moves forward. And so it just happens to be a fact about our universe that our universe is only homogeneous and isotropic in space. And in fact, that realization came as a quite significant surprise to physicists and cosmologists in the early 20th century, because until this point, the universe was assumed, for no particularly good reason, to be static. However, and I think it was assumed to be static simply for aesthetic or philosophical reasons, but the people who started thinking very carefully about the dynamics of the universe discovered that the theory of a static universe actually has two problems. So, first of all, as is clear even in Newtonian gravity, but is even more true in Einstein's theory of gravity, static universes are unstable to gravitational collapse. In particular, if you start out with a bunch of matter, say it could be hydrogen gas, if you want to study the formation of the galaxy or a solar system or something like that, then typically what will happen is if you have just a big pile of hydrogen gas sitting around, it might move in some complicated way, but it's going to tend to clump together. Gravitationally, the little bits of gas, all the different atoms, will attract one another, and they'll clump together, and eventually whatever matter you have sitting around will collapse together into some very lumpy and inhomogeneous structures, such as stars, planets, people, and so forth. And this general feature of gravitational systems to collapse is known in many circumstances as the Jeans instability. The Jeans instability is usually specifically described as the tendency of a cloud of dust, by which I mean just some dispersed matter, to collapse together to form a star. But more generally, people use it to refer to as the tendency of gravitational systems to gradually clump and become inhomogeneous. And indeed, if Einstein had really just considered the solutions of his equations for general relativity carefully, he almost certainly could have anticipated the later observation that our universe was not static and that it is indeed expanding. But I think even he found that aesthetically, a static and infinitely old universe was much more easy to think about than one which is evolving in time in some very complicated way. The other difficulty associated with a static universe is that if the universe is static and infinite in all directions, then the night sky should be infinitely bright. So let's think about that and try and understand why that should be the case. So let's imagine that we're sitting here on Earth, and this is us, okay, drawn quite accurately and beautifully, and we imagine lying on our backs and looking up at the night sky, okay, and there are stars that have been shining forever, extending infinitely in all directions. Then you can imagine thinking about those stars that are a fixed distance away from us. Okay. So let's choose some distance r and consider all those stars that are a fixed distance away from us. Okay. There'll be some number of stars that are a fixed distance away from us that will lie on the spherical shell, and they'll all be shining. And so their light will reach me, because these stars have been shining forever, because the universe has existed forever. And the total luminosity emitted by these stars, coming from the shell, can be regarded as a function of the radius of the shell. And there are two things that we should think about, which is, first of all, electromagnetic forces, and in particular, the intensity of light that is given off by a star, will decrease like 1 over r squared, 1 over the distance squared between us and a star. But the size, the area of the spherical shell, increases like the radius squared of that spherical shell. Okay. So if you imagine that you have some spherical shell at a distance r away from us, then the size of the shell goes like r squared, and in particular, the number of stars on that spherical shell will go like r squared. And that will cancel out the 1 over r squared coming from the fall off of the luminosity of light as a function of distance. So in particular, the total luminosity of light that we will see coming from the stars a given distance away from us is a constant that is independent of distance. And if we wish to understand the total luminosity that is arriving in my eyes as I lie on my back looking up at the night sky, I should sum over all possible radii, all possible distance, and I should find that, in fact, there's an infinite amount of luminosity, an infinite amount of light hitting my eye per unit time. Another way of saying that slightly differently is that if I imagine that the universe is infinite and has existed forever, and that the density of stars is uniform, okay, that's the assumption of homogeneity, then if I lie on my back and I point in a given direction, then in that direction there should be an infinite number of stars lying along that line that I'm pointing in. And because each one of those stars will give a luminosity that falls off like 1 over the radius squared, in fact, I'll see an infinite amount of light coming from that direction. Yes. Question?
Why do they assume that the closer stars can't block the light from farther stars?
Yes. Okay. Excellent. So Olbers' paradox was one of the great discussion points for the physicists and natural philosophers, which is what physicists were called before they were called physicists, of the 19th century. Indeed, people often tried to answer this paradox by saying, well, there could be, for example, some object in the way which is blocking out the light. So you could imagine that there is some cloud of gas, some cloud of dust. That's what people often attributed this to, because you look in a telescope and you see clouds of dust up in the sky. And so you might think that this would block the light. But then people responded to this by saying, well, if you have a cloud of dust that is sitting here and it's being bombarded by light, then it's constantly absorbing the energy from that light. And eventually it will get heated up so hot that that cloud of dust itself will glow with the same luminosity as those stars which it is obscuring. Okay. So this was the attempted way out of this paradox. And it was still something that people were concerned about and worried about even up to the earliest 20th century. I still think at the time, when people started making these detailed cosmological observations, people still believed the universe was static and infinite, but people didn't really quite know how to get around it. Einstein had one idea for how to get around it. Okay, Einstein's resolution of this was that he believed that the universe is is static and has existed forever, but finite in size. So he proposed what has now become known as the Einstein static universe, or ESU. So he proposed that space is actually not an infinite flat space, and not infinite flat three-dimensional space, but rather that space is a three-dimensional hypersphere. Okay. So just as a circle is a one-dimensional sphere, and what we usually think of as a sphere is a sphere in 2 dimensions. Einstein proposed that space looks like the 3-dimensional version of that geometry. So people will sometimes call this S3. It's the sphere sitting in 4-dimensional Euclidean space. It's kind of hard to wrap your head around. I've just drawn the usual 2-dimensional sphere sitting in 3 space here for you. And he proposed that the resolution of Olbers' paradox is that the universe is static and infinitely old, but not infinitely big. Okay? And so in particular, if you were to lie on your back and look up in the night sky, if you had a big enough telescope, you could eventually see yourself in the image of the telescope. Okay. So, for example, if you go far enough in one direction, you will end up back where you started. So just as if you were standing here on the Earth's surface and you started walking in one direction and you walked for a long enough, very long time, you would end up back where you started. He proposed that if we had a powerful enough telescope, we would be able to see ourselves in that telescope, albeit a very long time ago, because the light would have been emitted by, the light that we would be observing had been emitted by the Earth a very long time ago. And so this was his way of getting out of Olbers' paradox. However, he didn't resolve that first paradox, the first puzzle, that of the gravitational instability. And these two, the gravitational instability problem was only resolved when it was observed some years after the development of the theory of relativity that the universe is indeed expanding. But there was a question somewhere that I didn't answer, or maybe I answered it. Did you have someone had a question? No. Good. So it turns out that Einstein's model of the universe was invalidated, and indeed, essentially all of cosmology was invalidated by Hubble's observation, which is that the universe is expanding, and that, in particular, Hubble noted that galaxies are moving away from us at a velocity which increases with their distance from us. So in particular, if you imagine that you sit in some observatory and you look at some galaxy, then that galaxy will be moving away from us. So here v is the velocity of a galaxy. And it'll be moving away from us with some velocity that is a constant times the distance to the galaxy. And that constant that's appearing here is known as the Hubble constant. I'm going to put constant in quotes because as was later understood, and as we'll see in a few minutes, indeed, it is not a constant. Hubble thought it was a constant. And by dimensional analysis, you can see that it has dimensions of 1 over time. And in fact, it's a very, very small number. Okay. And so today, the Hubble constant is measured to be about 70 kilometers per second per megaparsec. Okay. That's a very funny set of units to use for something that goes like 1 over time. A more sensible set of units would be inverse seconds or something like that. But this is the set of units that people usually use to talk about Hubble's constant, because it's one that really gives you a feel for the scales involved. Okay. A megaparsec is 1 million parsecs. A parsec is a little over 3 light years. Okay. So the Andromeda galaxy, for example, is about 1 million light years away, 300,000, 200,000 parsecs. And so according to this law, it should be receding away from us at 10 or 20 kilometers per second. Okay. And in terms of galactic distances and speeds, that is very, very small, okay, which is why this was rather difficult to observe. I should actually make a couple comments about how this was measured. Yes, question. Hubble's constant is the same everywhere, but it turns out to be a function of time. Okay? And it turns out that the Hubble constant now is different from what the Hubble constant was earlier in the history of our universe. And you have to remember that as you look farther out in the universe, you're viewing the universe at earlier times. If you look at something 1 million light years away, the light that you're receiving was sent 1 million years ago. Okay? So when you see that a galaxy is 1 million light years away from us, is receding away from us at a certain velocity, you're really measuring what the Hubble constant was 1 million years ago. Now, Hubble thought that the Hubble constant was literally a constant. That's because he was observing galaxies that are relatively nearby, relative, of course, being the important term. So he was measuring the Hubble constant only over the last several tens of millions of years. But it turns out, as I'll describe to you in much greater detail, that over the billion-year time scale, Hubble's constant does, in fact, evolve in time. And we will write down the equations that describe exactly how it evolves in time. And in fact, one can derive them quite easily using very simple Newtonian physics. But before we do so, is there a question? No. Okay. Yes?
I would have a question about how did you measure the velocity of the galaxy? I assume we do it with light rays.
That's exactly what I'm going to. Okay, good. So I should say a few words about how exactly we measure Hubble's constant. Okay. So in order to measure Hubble's constant, we really need to measure 2 different things. So you need to measure the velocity at which a galaxy is moving. So in order to measure a velocity, that's actually relatively easy to do. You just use the Doppler effect. Okay. So the Doppler effect says that if something is moving relative to you, then light which is emitted by that object will appear either redder or bluer, depending on whether that object is moving away from you or moving towards you. And in particular, if the object is moving away from you, then the light will appear redder. And so Hubble's observation was, I think, I don't remember the exact year, 1919, perhaps. This was at a time when we were just beginning to understand spectroscopy. And as you presumably have at least heard, if you heat up hydrogen, for example, there'll be certain spectral lines that you can see in the spectrum of hydrogen if you split the light of hydrogen. And so what Hubble did is he measured the locations of those spectral lines, the frequencies of those spectral lines, and he saw that they were altered somewhat for distant galaxies, and that more and more distant galaxies were more and more redshifted. And in fact, today, when astronomers and cosmologists talk about the distance of a very distant object, they very often just specify the redshift of that object, namely the factor by which the light sent from that object becomes redder rather than specifying its distance in kilometers or megaparsecs or whatever. Question in the back. It's a speed, yes. Well, I don't know why you say angular speed. Well, okay. I mean, for an object that is moving, okay. Indeed, if you take a rotating object, like I don't know, I would say a record, but you guys don't know what a record is. Okay? It's an ancient technology by which people used to play music. Okay, and if you stand at the center of this quote-unquote record, then the points on the record are indeed moving linearly with the distance to you, but they're moving perpendicular to you, not parallel. So this is a slightly different setup where the galaxies are moving directly away from us at a velocity proportional to that of their distance. If you want to think about a model for this in your head, the best model I think that you can think of is to imagine a balloon. Okay, and take a balloon and draw a bunch of dots on that balloon. And each dot is going to be a galaxy, and the surface of that balloon is space. Okay, then inflate the balloon. Okay, and if you choose one galaxy to be us, to be our galaxy, and then you look at how the distance to the other galaxies are changing in time, you'll see that all of the galaxies are receding away from one another. Okay, simply because the balloon is being inflated. Okay, so that's what we mean when we say that space is expanding. That model is actually really not a bad model to keep in your head when you think about the expansion of space. The thing that's a little misleading about that example is that in that example, you can say into what the balloon is expanding. Okay? It's expanding in our three-dimensional space. But it's not the case that our universe is some three-dimensional geometry expanding into some four-dimensional space. It's just expanding. And you can't ask the question into what. It's just the statement that the distances to the distance to a galaxy is increasing in time with some rate that is proportional to its distance to us. Question.
Like an elastic on a ruler?
Yeah, like, or you could say like an elastic on a ruler. The other example that people often use is, I don't know if this is a better example or not. You could imagine that you have some dough, like bread dough, and you have a bunch of raisins in the bread dough, and then you bake it, and it expands, and all of the raisins get farther and farther away from each other. And so in that case, you're a raisin, and space is the dough. Okay, you can come up with all sorts of funny little things to think about when you think about this. I think the balloon and galaxies as points on the surface of that balloon, all receding away from each other, is a better model to keep in mind. Okay. Good. So it turns out measuring the velocity at which a galaxy is receding from us is relatively easy. But actually measuring the distance is actually relatively hard. Because when you observe a galaxy up in the sky or a star up in the sky, it's actually rather difficult for us to determine how far away that galaxy or star is. Because for all that we know, it could be a very dim star that's very close or a very bright star that's very far away. And so actually, the method that Hubble used, which remains one of the best methods that we have to understand how far away a galaxy is he used the fact that there are certain kinds of stars known as Cepheid variable stars, which have a very interesting property. So they have periodic fluctuations in brightness and these fluctuations have a period proportional to their overall brightness or luminosity. So it just happens to be that these are a family of stars whose brightness changes in time. And we know that the period of their oscillation in brightness is proportional to their overall luminosity, their overall brightness. And so by determining their period, you can then determine their overall luminosity. And if you know exactly how luminous an object is, absolutely, and you can see it there on the sky, you can use that 1 over r squared law to determine how far away it is. There's a question. No, it's actually different. It's a good question. So it's actually maybe just, I'll explain to you a little bit exactly how it works. It's different from a pulsar, although it's slightly different from a pulsar. It's much more of a normal star. So the way that it works is that it's sort of a funny, I mean, it's just one of these funny accidents in astrophysics where, so a star is a big ball of gas, okay? And there's different kinds of gases that can appear with different sort of dynamics in different stars. And a Cepheid variable star is a star where the opacity of the stellar atmosphere decreases with the temperature of the star. So what does that mean? Well, that means that if you imagine starting with a star where it's transparent so that the stellar atmosphere is not very opaque at all, it's very transparent, and that it will have some temperature, let's call it T, then because the star is very transparent, it's going to radiate away a lot of its temperature, a lot of its energy. And as it radiates away its energy, it'll cool down, okay? And as it cools down, it will become more opaque, okay? And because it's becoming more opaque, it'll decrease in size. And so it'll be very opaque. And it'll have a lower temperature. Or sorry, as it becomes more opaque and smaller, the temperature is then going to increase because it's more stuff compressed into a smaller area. So it starts out at low temperature, transparent and big, and then it will become smaller with increased temperature and more opaque. But then, as its temperature increases, its opacity will decrease, and it'll give off more energy, and it'll expand back to its original situation where it was transparent with low temperature. Okay? So it's the sort of cyclic property of the expansion and contraction of the star because of some quirk of its stellar atmosphere that leads to this feature. And the important fact about Cepheid variables is that we understand them extremely well. And even in the very early 20th century, this process was understood quite well. And so, for example, this was tested, this relationship between their luminosity and their period can be tested very well for Cepheid variable stars that are close to us. Because for stars that are very close to us, there's a different method that we could use to understand their distance, which is just parallax. Okay? Parallax is the effect. Parallax is the reason why when you close one eye versus the other, the image in the room appears slightly different. Okay. So for example, before Hubble, long before Hubble, people were measuring the distance to stars in our galaxy simply by understanding the relative positions of stars as the Earth goes around the sun. Okay, as the Earth goes around the sun, the Earth's position is changed by some, almost 200 million, 150 million kilometers. And so by understanding how images of stars shift on the night sky, you can understand their distances. And so for all of the Cepheid variables in our galaxy, we can use this to calibrate our understanding of how the luminosity of a Cepheid variable varies with its period. And then we can use that. So once we've used parallax to study the distance to stars in our galaxy, we can then use that to develop the theory of Cepheid variables. And then we can look for Cepheid variables in other galaxies and use our knowledge of Cepheid variables to determine how far away these other galaxies are. And this is then what allowed Hubble to correlate the distance to a galaxy with the rate at which they're expanding away from us. I mean, it's really a sort of wonderful and delicate story. I mean, very often this is the way that the history of physics proceeds, where you have some tools that you understand in one circumstance that allow you to develop other tools that will apply in much broader circumstances, and you can sort of pull yourself up by your bootstraps and understand some very, very interesting things about the world around us. Okay, are there any other questions about this? Yes?
Over what time scale is necessary to watch Cepheid to derive?
You know, that is a good question. I actually don't know the answer to that. So your homework assignment is to look it up. I'm sure it's on Wikipedia, and tell us next time. That's a great question. I don't actually remember the time scale on which this happens. Good. Yeah, and I should mention that even today in astronomy, measuring redshifts and hence measuring velocities of objects is very, very easy. But measuring their absolute distance to us is very, very difficult. Okay. So what people are always looking for in astronomy is what's a so-called standard candle. Okay? Because if you have a candle and you know it's standardized so that you know exactly how bright it is, then by looking at its apparent brightness, you can determine how far away it is. So in astronomy, people are always looking for standard candles, okay, by which they mean stars whose luminosity they know exactly. And the Cepheid variable was the first such standard candle, but since then people have learned how to use supernovas also as standard candles, and much of our most exciting knowledge about the universe today comes from supernovas. Yes?
How do you separate the intrinsic velocity of the galaxy from the...
That's a great question. So that's something that I was actually going to mention. I should mention, of course, that Hubble's law only emerges when we average over many galaxies. Okay. So each galaxy, in addition to having some velocity with respect to us due to the expansion of the universe, may also have some so-called proper velocity of its own due to just the way that galaxies are moving throughout space. So for example, just as planets orbit around a sun and the sun is orbiting around the galactic center, many galaxies form in clusters where they're all orbiting around one another. And so typically, if you observe a galactic cluster, you'll see that the different galaxies in the clusters all have different velocities with respect to us, because some of them might be happening to be in a place in their orbit where they're coming towards us. Some might be going away from us. And so you'll observe Hubble's law only if you average out over all of these effects. Okay? That's why I really say that when we talk about cosmology, we need to be talking about averages over scales much larger than those associated with a galaxy or even a cluster of galaxies. So that's a good question. Another question? Yes? What's that?
We're using candles to
Yes.
compare. So that means that the Hubble law must not be precise.
Okay, yeah, so there is an interesting story about how precisely we know the Hubble law. So for example, when I was your age and was learning about this stuff, people said Hubble's constant is something between 50 and 100 kilometers per second per megaparsec. Okay, it really was not known very well. It was known that things are expanding away from us, but the precision has really only been nailed down in the last 5 or 10 years. Okay, and indeed, if you want to understand, when we talk about Hubble's constant being 70 kilometers per second per megaparsec, we're talking about Hubble's constant for galaxies that are relatively near us, you know, a few tens of millions of light years away. When you talk about galaxies that are billions of light years away, you need to take into account the fact that also they're at some earlier time, and Hubble's constant was changing in time. And so, indeed, we really shouldn't call Hubble's constant a constant at all. It's just called that for historical reasons. It should be the Hubble parameter. Okay. And indeed, we don't know it completely precisely, and it is indeed dependent on time. Okay. So let me now try and describe this to you in a little bit more detail. Okay, yes, question.
The Hubble's parameter, is it increasing or decreasing?
It is increasing with time. Okay, we'll get. Don't worry. We'll develop the whole theory of it over this in the next 2 classes, I suppose. Okay. Okay. So another way of phrasing Hubble's law is that the distance to some galaxy as a function of time is going to be the distance now, which I'll call R0, times some factor that I'll call capital R of t, which changes in time due to the expansion of the universe. And this, of course, is an equation that is true in the approximation where I neglect things like small changes in the velocity of a galaxy due to how it orbits around the center of a cluster of galaxies or something like that. And the Hubble parameter, h, is r dot over r, where dot denotes time derivative. And indeed, that can have some time dependence. Depending on the form for big R of t. So just to place these observations in a bit of context, in the language of relativity, we measure the distance to some object by using the invariant interval delta s squared. And the statement that the universe is expanding is the statement that that invariant interval is itself changing in time. And in particular, if you have 2 events which are separated by some time interval ds squared and some spatial interval dx squared, then the statement of Hubble's law, the statement that the distance between objects changes in time due to the expansion of space, is the statement that the usual invariant interval of special relativity is replaced by the invariant interval that I have written here. And this model for the universe has a name. It is called the FRW model, named after Friedman, Robertson, and Walker. Sometimes it's called the FLRW model, including, I think it was Lemaitre. So t here is, of course, our usual time coordinate. And r is known as the scale factor of the universe. And it's telling us how the geometry of the universe is changing in time. So, for example, you can see that if you just take two events that take place at the same time t, but at different locations, then the distance between those two events, the proper distance as measured by this invariant interval, will change depending on the time at which these events took place. That's just a mathematical way of saying that space itself is changing as a function of time. In fact, the FRW can be made a little bit more complicated. So in this model, in the FRW model, space can be taken to be flat so that dx squared, so that the spatial part of the invariant interval is dx squared plus dy squared plus dz squared, namely the standard formula for measuring length squareds as given by the Pythagorean theorem, or it can be curved. In particular, it could be spherical, so it could be the three-sphere that Einstein thought was the geometry of space, or it could be a hyperboloid. So if I were teaching this class 15 years ago, okay, I would have to spend some amount of time telling you how to describe the invariant interval for these spherical or hyperbolic spaces. But as we'll see later on in this week, over the last decade or so, cosmological and astronomical observations have actually made it quite apparent that, in fact, the correct model to describe our universe is one where space is completely flat, so that you have the dx squared plus dy squared plus dz squared, as usual, appearing in the invariant interval that describes our universe at very long distances. Again, of course, I should emphasize that this FRW model is the model for a universe at very, very long length scales. So at the level of our solar system, for example, the geometry of